空にある何かを見つめてたら、それは推しだって君が教えてくれた。まるでそれは僕らみたいに寄り添うと、それを泣いたり笑ったり繋いでゆく。何十回何百回ぶつかり合って、何十年何百年昔の怒りが星自身も忘れた頃に僕らに届いてる。僕ら見つけ合って手繰り合って同じ空輝くのだって、二人だって約束した遥か遠く終わらないベテルギウス、誰かにつなぐ魔法。僕ら肩並べて取り合って進んでく。辛い時だって泣かないって誓っただろう。遥か遠く終わらないベテルギウス、君にも見えるだろう。祈りがどこまでいつまで生きられるか。君が不安になるたびに強がるんだ。大丈夫、僕が横にいるよ。見えない線をつなごう。僕ら見つけ合って手繰り合って同じ空輝くのだって、二人だって約束した遥か遠く終わらないベテルギウス、誰かにつなぐ魔法。僕ら肩並べて取り合って進んでく。辛い時だって二人だって誓っただろう。遥か遠く終わらないベテルギウス、君にも見えるだろう。祈りが空にある何かを見つめてたら、それは推しだって君が教えてくれた。
Good evening, and welcome back to TIS-100. Sorry, just reading the comments on my introductory music. Well, they do sometimes just sing things. Like, it happens. Only about half of the songs actually have dance routines choreographed for them.
Yeah, but you get the impression that about half of the remainder are improvised one.
And yes, and to be fair, that's not a K-pop song. As you might have noticed, it was in Japanese.
Wasn't really paying enough. I didn't actually look at what it was on the screen, so I couldn't even go, ooh, that's kanji, not...
Katakana, entertainingly, because it's Betelgeuse, which is obviously a non-Japanese word, or rather,
yeah.
Betelgeuse,
Right, yes.
which is slightly hard to spot.
Yeah, well, I wasn't going to be able to spot that it was that rather than Hangul.
No circles. Well, actually, it might. I can't remember. Anyway,
I could have spotted it if I actually looked at the screen for 10 seconds. But...
Where were we? We'd just done the signal pattern detector.
Goodness me, you got through a lot of those after I went snooze.
Well, I mean, there is the advantage that I've completed the entire game twice. Well, I completed the main part of the game twice. So, yes, now we have the sequence peak detector. Yes, the video had subtitles in Japanese and Korean. Japanese being the actual language the song was in, and Korean for the Korean audience. If you want the lyrics in English, you have to find another video somewhere. I think the one by the original artist will have that in. So let us create a new program for the sequence peak detector. Right. Sequence is a zero terminated. Read a sequence from in, write the minimum value to out.I and the maximum value to out.A. So it feels to me like the obvious thing here is we essentially have one processor that's calculating the minimum and one that's calculating the maximum. And here is our message from Uncle Randy. 2004-08-17. I am good, damn it. Just as good now as I ever was, but nobody want to hire old washed up Randy, not when all the young folks straight out of school will work 100-hour weeks for nothing. And I'm lousy at promoting myself, always was. Paul had Bill, was had Steve. I never had that kind of partner. Someone to champion me. It was always just me. I have, yes, everything's, so reminder that whenever you see anything green on the screen, that's actually in red on my screen. It's just in green for your ease of reading. I could probably do a cleverer job than turning it green, but it's kind of amusing turning it green. So, I kind of feel that we want to build in this one, we want to do something like, this one just goes mov up, down. This one goes like that. So essentially we arranged to split that this processor just tees the sequence in two different directions. That then plums it back down to that one, and then these two actually do the hard work. So then this one has a job of find the minimum in each sequence. So the awkward thing is how do we detect the end of the sequence? Because like the natural thing is to load something into the accumulator and then do something if the accumulator's 0. But surely the accumulator's where we want to keep the minimum we've got so far. Yeah. Maybe we can avoid doing that. I mean, we can mostly keep it in back. So maybe we don't have to. Let's see how that goes. So obviously if we're trying to detect the minimum, we want to start with moving 999 into ACK so that we're then looking for things less than that. We're assuming here that all sequences are of length at least 1. Because if they're not, then how are we going to send out the minimum and the maximum? You'll get 999 as the minimum and 0 as the maximum. All look to be positive, don't they? Yes. If you send us a 0 length sequence. So that we just do each time around our outer loop. And then I mean, actually, even comparing things is kind of difficult. So if we go sub ACK, I mean sub up, that's not very helpful. So that then tells me, then if what we've ended up with in the accumulator after we subtracted what we just got from up is still greater than 0, then that means that what we just received was greater than what we've currently got in ACK. I think I'm beginning to think this may be a job best split over more than one processor. So if we're so if we have greater than 0, then well, in that case, if we get less than 0, then the number, but then we don't have a copy of the number we got from above now. But I suppose we could have this processor start duplicating things, couldn't we? Feels to me like I want to do something different though. So there what I'm doing is I'm saying if but then swoop of course destroys what we've got in back, so we end up going swoop sav in this case, don't we? I suppose that works. Then actually we can move that L upwards to the sav. Temporarily don't send anything right. So what does that do then? So the bottom processor receives a 14, saves that in ACK, saves it there. Oh no, it needs to... Well, actually, that's perfectly safe. It's just stupid. Carry on doing the perfectly safe but stupid thing. So I was thinking I need to, if I decide not to accept a number, surely I need to read the second copy of it and throw it away. No, I don't. I can just not accept it a second time. That'll work perfectly well. Fewer instructions needed. More time spent processing things, but... So let's wait until the 0 arrives at the input of this processor. And then check if it's correctly found the minimum. Yes. There's a 0 and ACK contains 14. So that actually seems to work, except that we don't know what to do at the end of a sequence. And that's actually kind of annoying because is that going to be an entire extra complicated bit of code to receive? Because the thing is, we received the input twice. But oh. So after that instruction, no, but that's too late. That it's not too late, you know. If we insert in there JEZZ and stick a label Z down here that does that, then that would correctly, that's before we've saved the new value into back. So then we want the same thing here, but that's kind of amusing because does that then mean we could somehow share this code? Probably not, because we need that jump to be up there. but we've got enough space for it. Right, so can I explain what my code is doing now? It has essentially an inner loop and an outer loop. So the outer loop runs once per sequence and does mov 999 ACK, i.e. initialize the accumulator to a very large value, then some stuff to calculate the minimum, and then the minimum ends up saved in back and we pull it out and send it out downwards. So the inner loop starts at label L and has several jumps back to it. So what that does is it expects to receive 2 copies of each number in the sequence. So the first copy, it subtracts from whatever's currently in the accumulator, having saved a copy of the accumulator to back. And if the result is negative, that means that the new value doesn't change the minimum. And so it jumps to N, which then reads the second copy into the accumulator, tests if it's 0, and if it isn't, pulls the old minimum back out of back. On the other hand, if we don't take that jump, then we read the second copy into the accumulator, check if it's 0, and immediately jump to L, which saves the accumulator back into back, thus overwriting the current minimum. So that looks pretty good. So now I just need to do the maximum version, which is essentially the same code, but starting with mov 0 ACK, and that JLZ becomes a JGZ, and I think that's the only change. Let's add more plumbing here. We obviously need 2 copies of that instruction, just like we needed 2 copies of the mov ACK down instruction. So there's the 0 arriving in the minimum processor. Actually, we should have the, this one move right first to allow for the fact that there's slightly more lag, because it'll be easier to understand then. Okay, that did the output the correct 14 on that side, and the one on that side is about to do the same with 73. Right, that all looks pretty good. Let's just swap those over for prettiness sake. Actually, probably the right thing is not just to swap them over, but to interleave them, isn't it? That's going to be the fastest.
You're not telling me you have to schedule these processes.
Well, you can make things faster by changing the order of the instructions. I mean, they all pause synchronously to wait for one another as necessary.
Oh, right, yes, of course. You change the order of this process to stop that process of stalling.
Yes.
So if there's not, like...
There's no pipelines.
Within the process.
No, the processes themselves are very simple, but there are plenty of pipelines.
True.
Right. Yeah, I think you can fit 3 numbers in that input column. I mean, it does look like we're only getting 2-digit inputs, but I don't care. My code doesn't depend on that. Right. Surprisingly small number of used nodes. Surprisingly small instruction count. More or less average cycle count. I mean, I'm actually slightly surprised because my instruction layout is like the having 2 copies of the mov up ACK JZZ felt a little bit unpleasant to me. Well, 4 copies arguably, but no, it appears to actually not be too bad. I think this one is probably going to require some hardware we haven't met yet, because reversing something is going to require remembering it, and it's not like we have much by way of means of remembering things yet. Maybe I shouldn't be typing in IRC, I should be talking. But we do indeed have shiny new equipment. We have two stack memory nodes, which appear in the manual. And what they do is
If there's no card outside, I'm going to go to the stick box.
is this. Whee! And they will absorb numbers and they will spit them back out again in the reverse order, which, when you want to reverse things, seems like a pretty good plan. So what message do we have from Randy, which I fear is getting more and more detached? 2004-08-20. When I get into a groove working on this machine, it feels like I'm in the presence of a being that understands me. Forget all about life that pains me and drags me down. I want to be a tessellated intelligence. Take inputs, process. Take inputs, process. Take inputs, process. Perceive. Understand. So, yes, Randy is trying to turn into a tessellated intelligence. So what are we actually meant to be doing anyway, now that I've waved the exciting new hardware? Sequences are zero terminated, read a sequence from in, reverse the sequence, write the sequence to out. Right.
Is there an upper bound on the size of sequence you'll give it?
I think we can assume that the upper bound will fit inside a stack memory node.
Ah, yes. Right.
So it's about 20, I think. It would be rude to, on our first introduction to stack memory nodes to be required to work out a way of splitting the sequence between two of them.
True.
I mean, I don't know quite why they've given us two. Obviously what this means is we need to do something like this processor up here reads a sequence into this stack memory node and then somehow signals to some other processor, or indeed possibly signals to itself to read the sequence back out of the stack memory node and send it off to out. Right. We might have some groceries very shortly, in which case will be forced to leave you with some Yunhar simply because I, as I said, have nothing else musical to provide. But I mean, I have been listening to some Promise 9 this week as well, but I think I've probably played almost all of the good Promise 9 already. So we at the very least need this node to notice when a 0 goes past, don't we? So it's probably going to need to copy data into the accumulator. I think this is co-Yunhar, not Yunhar Lee. Yes. So yes, probably the same name, but quite different people. So then we need to go F for finish.
How many orcs? I said, how many orcs?
How many orcs must the road walk?
So then wonder what we do when we reach the end, because obviously, that bit is obviously correct for read a sequence into the stack memory node. Um, so then we mostly just need to read it back out again, don't we?
Biggest problem is sending a signal in some annoying pattern down to.
Well, I mean, this one can do the reading as well. It'll be we have to stall the writes until the sequence has been read out anyway, because otherwise we'll all end up in a horrible mess. So lovely though it would be to be able to parallelise this, I don't think we sensibly can. Obviously, what we then do is we take advantage of the two stacked memory nodes, and while we're filling up, while this one is being emptied, we're filling up this one. So that would be the.
Well, I guess the next challenge is to implement a queue using the two stacks. In a nice Okazaki fashion.
So yes, we can. So actually, the twiddly thing here
It does.
is, how do we know when we've reached the end? Because if you try to read from an empty stack memory node, you just stall, waiting for it to have some data in it.
You can push a 0 first.
Oh yes, that's a nice plan, and then we can take advantage of that and not have to send an explicit 0 at the end. Nice, yes. See, the silly thing is, I've done all these puzzles before. I've almost certainly come up with that idea, but could I remember it? Mov 0, right. Stick a known elephant in Cairo.
That makes sense.
Yes.
What? There's some ancient piece of programmer humour that says, in order to search for a lion in Africa, you write
Elephant, surely.
So, yeah,
Or is there some more extra complication I forgot?
in my version it was a lion, but yes, in order to search for an elephant in Africa, you iterate.
You start in Cape Town and work your way north, checking everything you find to see is it an elephant or not.
Right? Note, experienced programmers will place a known elephant in Cairo to ensure that the algorithm terminates.
And the thing is, of course, that this is liable to be quicker than merely having any like range check or anything, because you're already checking whether everything you find is an elephant. So you don't need to check, am I in Cairo? Is this an elephant? Repeatedly. You just check, is this an elephant? Right, so then what we need to do...
If you get to Cairo and find an elephant, then what if there were two elephants in Cairo and you find the first? Do you report success or failure? I'm not confused.
Well, yes, really you want to place a known elephant just off the coast of Africa in the Mediterranean.
Yes.
And thus we need to check whether the standard allows you to have a pointer to just off the end of Africa.
I think you should actually start at East Africa and work your way across. And then when you find an elephant at the far tip, you can report West failure.
Thank you, Simon.
I thought you were going for an Ivory Coast spot.
Well, I mean...
Puns are endless. I mean, hopefully we'll turn this out staked by
Right, anyway.
actually ringing the doorbell. But
So then our second loop goes right at
I don't think it's loaded.
That's very disturbing.
down
This laptop
JEZ.
suddenly goes down
T.
because it was really concerned about its processor overheating, but it was making my knees chilly. I think it overestimated the amount of heat it had to dissipate.
You overestimate my needs.
Did I ask for tea? No. Oh well.
we'll probably arrange for there to be tea while we are carving it.
Yeah. Right. So that. I mean, is that right?
It's a strange disturbance in my knees.
That's obviously stupid. That should be JNZF, but I mean that looks like that might be correct.
From a certain point of view.
Well, I mean, I suppose we do actually need to my labels. When I choose the letters for these labels, I have some kind of idea in mind about what they mean, and then I change the program, and they're completely meaningless. Right, that might work. Let's single step it through one reading writing process. But obviously, it won't work though because I need to actually put in the code for these ones. Right.
There's stuff outside the door.
So that's correctly filling that up. And then emptying again. Yeah, right, that looks good. Well, let me hit the run button and then we can go and sort out our groceries.
Then you can hit the music button.
There we go. I'm slightly surprised that that was a good cycle count. I now really want to try the parallel version to see how far down the cycle count goes when I do the parallel version. Well, let's return to the segment list because I should probably do the parallel version separately and I should do it after we have sorted out our incoming groceries. So we will see you later, and if I'm really lucky I have a button here that sticks some copyrighted music into my stream so that I can ask YouTube to cut it out later. And it goes like this.
가지 못해 지난 그 길론 움켜쥐지 못해 흘러버릴 뿐 지금이 아닌 언젠가를 그리워하는 나조차도 봐 그때 내가 아니니 I wanna know what in the world's going on 결국 끝을 향해 가는 비극이라도 Walk and lock the door Tell me how I'm trying to be a piece of me 발 맞추는 시간 속에 기록했어 No process freeze and the reason why 거기 없어 the process A reason and the reason why I was lost without you but it had to 거기 없어 the process reason and the reason why Someone to try to stay alive but they're gone out of sight 남겨진 내 몫이니까 I'm still being alive 걱정을 가지는 거짓들에 뒤엉키고 속지 않도록 난 그만 바라보겠어 I wanna know what in the world's going on
Hello again. I really need some kind of a countdown to Ben is going to be back in 10 seconds so that you know to pay attention. Maybe I should start now. 10, 9, 8, 7, 6,
Mission sequence start.
5, 4, 3, 2, 1.
Go!
Hello, I'm back. Right. I'm actually still reading the IRC scroll back.
It's okay, we're only whittering.
Yes.
It's true. The wittering was certainly quite wittersome.
Yes, I apologise for not implementing an entire automatic DJ for filling in for me while I'm away. So, while I have technically solved this one, I kind of feel that the fact that almost no one seems to have done a parallel version means I should have a go. So, do I actually... Maybe I start by copying the previous one. Right. Yes, Jacob, I have occasionally thought that my startup thing should have a countdown that says TIS-100 follows shortly. A gradual thing going downwards. It doesn't work quite so well for end of doing the groceries because I can't predict that quite so accurately. But I mean, I suppose I could have had a second interlude track queued up so that I could then switch to that, something short.
Hey, this is computer programming. Everybody knows that you don't expect progressometers to be accurate.
It's true.
I mean, I do have a reasonable number of like 1 to 1.5 minute K-pop tracks that are intros to albums and such like. Some of them are quite good. Luna 1/3's Into the New Heart is surprisingly decent. Anyway, so what's our stupid plan then? So the stupid plan is that once we've filled up this stack memory node, we then start sending the next sequence downwards and into that stack memory node.
Oh my god.
And meanwhile, signal to this node that it should start reading the first sequence out of this stack memory node. And once that one's finished, then we signal to this one that it should start reading the next sequence out of that stack memory node, while allowing for the fact that the sequences might be of different lengths so that everything has to wait until everything's ready.
I've got what we're waiting for now.
So, oh gods. Right, well, I mean, surely this can be done. So we have the nice feature that all of our sequences are positive. So we could use negative values for signalling if we need to. But like for the first step, essentially, it's the moment we start getting something coming downwards that we know something's happened. So we already have that JEZF that sends us down to here. So presumably that means this one never reads from the stack memory, so we can throw away that code and, well, it'll end up there eventually. Hush. Right. There. So this one, once it has fed a sequence into the stack memory node to the right, then needs to start doing basically the same thing downwards. Doesn't it? So it does something like, and it does want to send zeros downwards. So it wants to do something like that. So let's see how that looks as like a start, ignoring those processes over there. So we load the first sequence into the stack memory on the right. That's wrong, that's jumping to the wrong place. Yeah, I could use a breakpoint. I'm sure you don't mind the strange clicking noises.
They were accelerating gradually at the start of your debugging session, in a way that made me suddenly think of the downward spiral.
So there are various things wrong here, but it seems like a reasonable start. And at least some of those things are actually that we want to put more complexity into this node. But we've successfully got the first sequence over here correctly zero terminated at the top, and the second sequence down here incorrectly terminated. So then the intriguing thing is that this one then has to wait for this one to have finished reading from the stack. So I think we may end up with things being a bit more synchronous than they strictly need to be initially, simply because, oh gods, the asynchrony. Like, I can't currently see how we could make them work properly otherwise. Well, let's see what we can do. So that is as far as it goes, all right. So this one I think needs to be enhanced a bit, so that it should actually do something quite similar to the first loop there. Let's start by initializing this to the same thing, except that obviously instead of right we say down. And it doesn't have that second loop. And there is actually an extra complication that I need to implement instead. So that should now correctly load up the sequences with both of the stack memory nodes being properly filled. If we carefully don't step beyond here, because otherwise I'm going to stick the wrong thing into here. Right, so that's good. So now what we need is when this one receives its first byte from above, it should signal to this one to start reading out of that node. So that mov left down is of no use at all. That obviously has to read from up. So the simple way to have this synchronized is that this thing will send some rubbish byte rightwards, which this one then sends downwards. I am now, of course, going, but why are we sending a rubbish byte? Could we not have this one send the last byte of the sequence as the token somehow? But let's not get ahead of ourselves. Obviously, or maybe send the negated. No, if we knew that the first byte we received was actually the last byte of the previous sequence, we might be able to do that and thus make things a little more efficient. Let's not try to be efficient yet. Let's try to make the bloody thing work.
My brain's just come up with the phrase last byte of the proms.
Yes.
Optimization is the root of all evil, etc.
No, actually, I think this simplifies. It simplifies some things. Oh, but this one's not going to have that. This one would have to read it back off the stack, wouldn't it? That might not be very expensive. Well, the thing is that otherwise, this processor has to read a byte from above and know that the first time it does this, it should send a signal to the right, and thereafter it shouldn't send signals to the right, and so it needs to have a separate instruction for that first byte. But if it's going to have a separate instruction for that first byte, it may as well be a more useful one. Right, so what that would mean is that where that jumps to F, it should instead jump to E, which is obviously the correct name for the label just before F. And that does a mov right down. So that picks up the top element of the stack. Then this one will then mov up right, which is the signal to switch the entire system into read out from here right into there. This one can then mov left down, and then it starts reading from this stack memory node. Now, I have got the slight thing here that now I'm assuming all of the sequences are of length at least 1. Yeah, all the test cases are... Oh, no, they're not. They're not. Zero length test case. Zero length test case. I can't assume that the sequence has a last element. Okay, right, I have to do it the boring way. Right, so we can't do that trick. Instead, well, sod it, mov nil down. Mov up right, mov left, nil. There we go. Precisely the same code. We just read a byte of rubbish and pass that around.
Nil is a reader 0 ignore register.
Yes.
But you can't use an immediate 0 to get a reader 0.
Oh, I could use an immediate 0.
Okay, so nil is
Yeah, well,
nil is only readable because who cares?
Yeah, I mean, and for my purposes, yes, because the instruction set can obviously encode read from nil. In my case, I think it's a convenient documentation. It says this is 0, but nothing cares that it's 0.
Yes, which is something I don't care about rather than something that's...
I'm really treating it as void.
Yes. Unit.
Yes, that's more correct, because of course void is the type with no values.
Well, no, I mean void as described in C is the type is the unit, but well-ish. I mean, only syntactic nonsense. But the point is, a function returning void is allowed to return.
Yes, true. Yes. Whereas I know Rust has treats types with no values as precisely something you can never return.
Yes.
If your function returns something of type of a properly empty type, then
the ridiculous thing about the empty type is that if you can detect whether a type is empty by considering the type of functions from the empty type to it. Because the only thing you are allowed to map the empty type to is the empty type. So the type empty to X is empty if and only if X isn't empty.
yes. Anyway, right. So that does mov x nil, mov left nil, mov up act, mov act down, JNZ back to there. Otherwise, we wait for another signal. That processor looks pretty good already. Good. That one is currently just saying mov up down. That will work until we start needing to read from here, at which point we need another batch of signalling. But let's see, this should thus read out the first sequence reversed, and do so while reading the second sequence into the second stack memory node. So first sequence reading into the first stack memory node. We've reached the end of the first sequence. So we signal across there and start reading out the first sequence in parallel with reading in the second sequence. Looks good. And we finish reading out the first sequence, and then everything goes pear-shaped. I'm not even going to run it any further because I don't really care what shape of pairs it ends up being. So,
If you did, you could hold a conference to find out.
thank you, Simon. So, the next job is what do we do once we've finished reading that out. So this processor will then stall, waiting for its next signal to start readout. That's good. This one, I think, needs to start counting through. So this one needs to get a signal, but its signal is going to be the first one that has to pick out a signal from in amongst an actual sequence of data. Every one of our previous links has been either a data link or a control link, essentially. This one's a bit iffy because we send a control signal right at the start and then start sending data, I suppose. Maybe actually that just means... But this one is pure control. This one's pure data. This one's pure data. This one's pure data. This one, I suppose, by symmetry, must be working the same way as that one. So all I need to do is work out what that means. So... what does that mean then? So what is the... So yes, this of course does read out a sequence until we hit the 0, and then actually it needs to wait for something which it doesn't yet know how to wait for, but we'll keep quiet about that for now. Well, actually, it might not turn out. We'll see. Don't think that far ahead. Except, of course, that this one does have to think that far ahead. So this one can start with something that looks like vaguely similar to that. Except, of course, it does actually want to do... it doesn't look like that. It wants to look more like that. That's kind of pointless. So, mov left ack? No. Mov up ack. So, read the sequence from up until you reach a 0, then stop. So then what do we do? Now what we need is some way of signalling that this stack memory node is ready. Because obviously if we have a short sequence followed by a long sequence, we might have finished reading out from this one before this one is full. So once we've finished that readout, then we need some signal from here down to here to say, right, now it's your turn. So can we just do that by going mov nil right there? And then here going mov left down, and here going mov up nil. That looks like it's feasible. So then we just do basically the same thing. Oops, no, you can't middle button paste in this. But from left, obviously the thing that comes after L is M. I'm sure that won't cause me any confusion. Right. Well, there's like a 10% chance that this code is now entirely correct.
And a 90% chance it will drop all the bits on the floor in a hilarious fashion.
So read in the first. I think there's somewhere around the like once we've read the first two things.
I just realised that afterwards I carry on that sentence.
So first sequence being properly read out, second sequence being properly read in. Good.
State covered in eye drops. Again.
So that's the first sequence fully sent out. And we've correctly determined that we've terminated that. Oh dear. So we found a 0 from somewhere.
Proper 80s noise that was.
Where did that 0 come from then? Is this silly thing writing zeros, terminating the contents of the stack with the zeros?
Silly thing in reverse.
So that looks fine. We've got the second sequence correctly in there. Ah, but then this immediately falls through to MOV 0 down. Yes, I see.
Really, the combination, isn't it 43 quadrillion or something? Hang on, it's several 1 billion.
Yes, so the problem is that this one is not... This one should then wait until it's signalled
He said that
to do something.
understatement was akin to McDonald's advertising over 3 served.
Yes.
So let's see what's going on here. This one signals that one's ready to read, but then it immediately starts trying to fill it up again, and that's obviously silly. Well, let's go for the simple approach. I think this is incorrect, and I hope that the tests will prove it. And just put those in the other order. That's obviously wrong, but it might get us a little bit further. How intriguing. Where did that 0 come from? Seems like that's the general style of this thing. I single step for a while and then go, where did that 0 come from?
You want to be able to single step backwards.
Yes. This machine comes from 1979. They hadn't invented time travelling debugging then. Or whatever the correct term for it is. Right, so our problem is actually that bit's still wrong. This node is writing into the stack memory too early. Right, so there's a general problem, I think, that we need something that signals from this node back to that node, that it's safe for this node to start filling up that stack memory again. So at the point when this does that MOV left down, that's the point at which this node then just sits there until it's time for it to start copying from up to down. So it's fine for it then to do MOV down left as a way of taking a signal back again. That node is going to be quite happy with that experience. Similarly, this one is not involved in that data flow, and so it can here wait and do MOV right nil, and that will be fine. And that then means that this one, when it finishes copying out, here should go MOV nil up. Right, let's try this. See, just thought, one of the things that I've liked so far in TIS-100 compared to Shenzhen IO, I haven't run out of instructions in a processor. I mean, I think I do eventually, but like, they're fairly generously proportioned, which is nice. Right, so now these two are both stalled waiting for this one to finish reading out this node. This one, on the other hand, is still happily running, pumping the next sequence in up there. So that's all looking quite good, really. And then bottom right node signals upwards, signals leftwards. Then signals go back again. We pick up the beginning of that sequence and start loading the next sequence into there, though I think that one turns out to be empty. So there's a kind of rather boring thing. Now we're loading a long sequence into the top right. And so actually everything ends up now stalled, waiting for the next sequence to finish loading. This is working. Right, should I hit run? Yeah, let's do it. Yay! Oh dear! Right, so our first test run completed entirely correctly.
And then there was a giant explosion.
Then there was a giant explosion in the second test run. But it recovered.
Yeah, that is odd, isn't it?
Like, so is it just like, well, I suppose it's not surprising. The whole system doesn't lose numbers.
Yes.
So it will tend to permute them.
It has, in fact, yes. It moved the 62 down to the end of
Wow,
one
yes.
sequence and the 34 down to the end of the next but one sequence.
Right,
So
that's,
there's
that suggests we're accidentally leaving something behind in a stack memory
and
node.
it's the same stack memory node both times because there's a sequence in between.
Uh-huh. Right. So let's let this run through the first set. Ooh, something went weird there. What's that doing? That's not allowed. So that's ended up reading an extra 0 in. That means this isn't waiting for something, isn't it? Doesn't it? Yes, yes. We've yes, because we've got we've got the backwards signalling sequence here set up, but we haven't got the backwards signalling there set up. Right. So that's what's going wrong. Right. Where's so when this one passes here, we need it to signal back up to there. Well, let's assume that we do that in the same way we've done it every other time. We need this one to signal, I have finished reading. Now it's time to, now it's safe for you to write again. Right, so presumably that means I now want to mov write up somewhere in this program. So it's going to want to happen. I think that means it happens here. Because that's just our, yes, I think that's it. Because that, if nothing else, here we have mov nil left, mov left down, mod down left. So obviously we need the corresponding sequence of 3 instructions here. Mov right up, mov nil right, mov right nil. And then here we just need to add a mov down nil at the right moment, which is just before we go back up to the top and start refilling. So it's here. Yes. Well, we're at least well over to the left of the cycle count graph now. If well to the right of the instruction count graph.
Well, yeah, you can't have both at once.
No. I mean, obviously the cycle count is still not optimal because there's still a lot of synchronous switching things between reading and writing that could actually maybe it can't sensibly be made asynchronous. I'm trying to work out if by just watching this thing I can tell that there are obvious unnecessary stalls. I'm pretty sure I can't. So yeah, I'm quite pleased with that. That's got it a good deal faster. 268 cycles instead of 343 cycles. Oh, and my note the things in these histograms show my best in each case. So they kind of lie. I appear to have achieved 11 instructions and 268 cycles, but that's actually I've achieved 11 instructions in one implementation and 268 cycles in a different implementation.
I wish you hadn't broadcast that on YouTube. No end of marketing development is going to be picking up that little trick.
Kind of feel sure it should be possible to... Oh God, you can make this one with one fewer node. You really shouldn't. Because I think you can do this. I think you could use that stack memory node as a pipe.
Oh.
There we are, 3 nodes.
Okay, that's the sound of steps being moved by a table table.
Right, 10 instructions, 3 nodes, which puts me off the left of the node count graph. Yes, so previously I had we have these three nodes that just did repeatedly read from above and copy sideways, and then read from sideways and copy down, and read from up and copy down. And I realised that a stack memory node will block if you try to read from it when it's empty, and as soon as you write something to it, it will become readable. And so if you have one node writing to it and another node reading from it, it acts as a pipe, except that it's free, unlike a node with a mov instruction in it. So yes, that thus saves that thus. No, I can't do it with 2 nodes. That doesn't work. Because fundamentally that means they have to be those 2 nodes, which means that they can't talk to one another at all. So yes, there we are. Actually, I'm kind of going. Can I shave any more instructions off this? Probably not. Not really, no. Actually, I can make it faster. I think it does cost me an instruction, though. Unless I can kind of turn the loop backwards. Well, what I'm thinking is that mov0 right, when the accumulator... Oh, does the... No, the... Yes, when the accumulator necessarily contains 0 at that point. Now, that doesn't actually help me, does it? Because I was thinking this mov up ac and then later mov0 right. Can we not make that part of a mov ac right? But no, we can't because everything's in the wrong order. So I don't think I can make it faster like that. Because we're just moving from ac, which, yes, we already have. So the only interesting thing is can I pervert this loop? If I make the loop go back to there and make that mov ac right, and then we have to move that JEZF, though that doesn't work. No, because then this is just not a sensible plan, Ben. Because then we'd end up with everything being backwards. Because we would have to start with the JEZF. Why would we? Can't we put... If we was planning... No, we would have to put the JEZF... No, hang on, what? Let me try that again. So, the plan is we change that to mov ac, right? That will work, right? Won't it? Because ac is guaranteed to be 0 at that point. But now we have something which does mov ac right jump L, but we could instead move L up by 1 instruction and remove that mov ac right. And surely all I've done there is hoisted that ac up to the top of the loop, so I shouldn't actually have changed the semantics at all. Right, excellent. We've shaved one more instruction. Well, she shaved an instruction off. It may not actually be any faster. I'm not sure. 343 looks like it's the same. Yeah. But obviously, JEZF jump L is equivalent to JNZ L when F is the next instruction. Yeah, pretty sure that's as efficient as it can get. I can't see any of those instructions that spare. Right. 314 cycles at the left edge of the cycle graph, 3 nodes off the left edge of the node count graph, 8 instructions off the left edge of the instruction count graph. Where off the left edge means below 1 pixel's worth of people have achieved this. That's pretty good then. Right, what have we got next? Signal multiplier. We don't have a multiply instruction, unlike in Shenzhen IO. Wow, this one has a lot of different implementations.
Gosh.
Cycle counts from that's going to be somewhere around 200 up to over 3,500. Hello, Uncle Randy. 2004 0831. At first I thought the TIS-100 was esoteric and strange, but the design makes so much sense once you get it. It's like it was designed by a different kind of intelligence. Completely different from the computers we know, but familiar too, in a way. I don't believe in New Age bunk, but it's almost as if from a universe.
Obviously you don't believe in New Age bunk. Any part of it you believe in, you won't describe as bunk.
New Age bunk. See, whereas I go, well, it kind of reminds me of what little I know of a transputer. It's not. Maybe transputers are from another universe as well. On the other hand, I suppose the weird decimal arithmetic is fairly... Well, that might just be like 60s IBM. Yes, see, Big Beast, I know that I can do all of this, so... Right, read values from in.A and in.B, multiply the values, write the product to out. Well, that should be quite simple. Why the hell do we need 2 stack memory nodes? I mean, probably that's when you want to start making it actually fast. Because, like, there's an obvious slow implementation, I think. Yes.
So what levels of multiplier sophistication can you fit into all this? Russian multiplication might work. No, I suppose you can't divide by 2, can you?
No, we don't have division or shifts.
So actually it's going to have to be iterate adding this thing that many times.
Well, that's certainly how I'm going to implement it initially, unless you can think of a better plan. So, I mean, the really simple thing would be... No, not T. I think actually I end up using my old friend JRO, don't I? And I have 2 micro instructions, one of which is... No, no, I have to be more clever than this. Because the obvious thing is have this one go into a loop, signalling repeatedly to this one that it should add something to its accumulator. Except what can it add to its accumulator? It can't add from up, and this one doesn't know the thing that it should be adding repeatedly. So I think we need extra complexity to accomplish this. This is now getting into the what I think of as the classic TIS-100 design, where you end up constructing a pipeline of processes that each do a tiny bit of the job.
It's not that different from the Shenzhen IO.
Yes. Though in this one, yes, you often end up with them essentially microcoding the next processor. So maybe we can do it more interestingly, but we need a processor whose accumulator can repeatedly emits B, say, and one that then accumulates the results. So I'm putting in these labels even though I'll never call them, simply so I can remember where that JRO is allowed to go. Actually, no. Let's make that a JRO at the top in the really obvious fashion. Let's not make this complicated just yet. Complicated can come later. Curious, are you allowed to have numbers as labels? Yes. That seems a much better label for the beginning of the program. Actually, of course, then what I can do is I can put numbers here to tell me what to put in JRO, what to inject into the JRO instruction. I mean, I'm assuming that I actually have to put the label in. Yes, it does. 0 there is actually being a label and not an absolute address. Amusingly. Right. Well, we don't really need a jump 0 at the end. So then this one... No, hang on. No, let's stick to that. So now at the end, so that will now. Oh right, yes, okay. Actually, let's. Partly because I think that's going to be what the next instruction is going to be. That, of course, is now waiting there. So then this we'll start with a program that just goes add up. Actually, if I just hit run, the system will crash at the point when this contains the wrong answer. Nice one. What have I done wrong? I mean, the first thing is we multiply 1 by 8. So we start by loading 1 into the accumulator on here, 8 into the accumulator on there. That's a pretty good start. Then we send an 8 downwards. Why is that doing mov up ACK at that point? That's utterly rubbish. Right, let's try that again. Run. Right, now we have correctly got the answer to the first question. What is 1 times 8? In this processor's accumulator, it is 8. So the problem is that this one, of course, if we can't know when to stop adding from up. So we need this one to also be microprogrammed. And one of its operations is add up. And one of its operations, which will actually make the first one, is mov ACK down. So then, of course, that means that this one has to start signalling to it as well. So let's just put a plumbing node in there. So at the same time it signals 3 right, it should also signal 3 down, and then this should signal 1 down. Right. That seems to work. Okay, all of our sums but one are wrong because we aren't resetting the accumulator. And obviously that is now instruction 4, so we need to change that 3 to a 4. So it's not the most spectacularly efficient in terms of speed,
But the most enthusiastic.
but it seems fairly efficient in terms of number of instructions. So essentially,
Ooh, yes, that's chugging noticeably. Isn't it?
so essentially what I've got here is these two are each have a bunch of, well, 2 operations, one of which is the accumulating operation and the other of which is the you've got a result operation, and this just sends suitable numbers to each of them in order to tell them which operation to do at each stage. I may have to press the fast... No, we've only got 2 more passes. Let's let it run at standard speed rather than ludicrous speed. So our limiting factor is the speed of this processor here. Damn it, Simon's not going to stay and tell me how to do faster multiplication.
Well, I do have like time to walk home as well as.
Yes, that's fine.
Um, yeah, I don't know how you do faster.
I mean, blatantly you can. Someone, like, it's not just someone has. It's clear that this is the solution everyone or at least a solution pretty close to this is what everyone comes up with.
I don't suppose it helps if you decrement each number 1 by 1. No.
I mean, you could have some slight extra efficiency by working out which way round, by swapping the numbers over if it looks like it's going to be better to do them one way round than the other.
Yes, you could iterate for the min thing.
But yeah, we don't have...
I mean, I just had the stupid idea that you, given A times B, you accumulate an instance of A, decrement B, and then swap them round, and then you're decrementing them 1 by 1, but that surely isn't actually better.
Now I'm just trying to work out what you're actually doing there. Is that like doing multiplication by constructing 2 interlocking triangles or something?
I think it is, yes. Yes, you're trying to make a rectangle, and you take a row, and then you take a column of what's left and a row of what's left.
Yes. Which does give you the minimum of the 2 in terms of operations.
Jacob is making suggestions.
Oh dear.
Yes, Jacob, the problem with shift and add, in order to know whether to add each shifted version, you have to test the nth bit of the other number. A shift left is easy, you just add something to itself. But the problem is you can't tell out of the other number which the...
Yeah, because we only have nop, mov, swoop, sav, add, sub, neg, various kinds of jump, and that's it.
there isn't a parity test among the jump?
Good question, but we only have equal to 0, not 0, greater than 0, less than 0. And
This does remind me of the spell book in the sorcery epic.
lots of 3-letter things, yes.
Z.
No, that's true.
So, I mean, loop unrolling is thus a possibility. I think you might be able to do some stupid loop unrolling with JRO. Now looking at what numbers we get. They're all pretty small, you know. They're all small enough that you might be able to do everything in this processor in an unrolled loop.
Jacob, on your other suggestion, I'm sorry to say that Montgomery multiplication is completely out of scope. That is not a technique for doing multiplication in the first place. It's a technique for doing fast modular reduction. If you have multiplication that is much faster than your division, when you have neither to begin with, and don't need modular reduction.
I mean, yes, I suppose.
Oh yes, giant lookup table.
It's true we have 9 nodes. We know that every input is single digit. Oh God. And we have at least 9 instructions per node. Oh, but we need to jump back to the start in each case.
So hold on a minute. Hold on a minute. You don't... We may not be able to test bits. You could do a shift and add, couldn't you? Because you can keep adding A while subtracting 1 from B. But if you start by computing 2A, you can keep adding 2A for as long as you can subtract 2 from B. So what you do is you start with A and a value to add. You start from A and 1, and you double both until your 1 is doubled to the point where it's bigger than B, and you put them in the stack nodes, and then you repeatedly pull out of the stack node a thing to test subtract from B and a thing to add to the accumulator if so. Yes.
I have the slight problem that I can only half understand your suggestion.
So, okay, you take your A number and you take 1 and you put them on your stacks.
Right.
Then you put 2A and 2 on the stacks. And then you put 4A and 4 on the stacks, and so on. And when the thing on the right stack is bigger than B, you can stop stacking stuff.
The right stack being the one you were putting
1, 2, 4.
1, 2, 4, 8, yes.
So you filled up your stacks with powers of 2 and those multiples of A in parallel. Now, pull the largest power of 2 off the right stack. If it's less than B, then subtract it from B and accumulate the corresponding multiple of A. Now what you've got left in B is guaranteed to be at most the the sum of all remaining powers of 2. So you pull the next smallest power of 2, subtract from B.
Yeah. Noting that we actually have to subtract because that's the only way we can compare, but that's not a serious problem.
Right. I mean, if you
right. Yes. Okay.
Subtraction has gone negative, then I guess you have to compensate by adding again or something.
Yes. Which is slightly tricky because we've just lost the number that we were subtracting.
Well, then you've got.
But we can save it in back and swap it back out again instead of adding.
I was going to say you've got a spare processor that can
Yes.
pull the thing off the stack and throw it to the left twice.
Yes. Okay. Yes, that's an idea of a multiplier. Right. I think I can remember that. Right, yes. So Simon, having given me what I'm going to be doing for the next hour,
Stop it. Shift and little break. Oh, yes. These are right next to each other. Usually, I mean, they don't really want to part on them. No, they're normally side by side, so. To an extent.
well, I think since that one worked, right, entirely new program because this is in no way going to be related to the previous one.
Good night.
Actually, sod it. Let's not worry about B, the value of B for the moment. So if we have that, that writes the powers of 2 into that stack memory node. Obviously, there's not much point in going very far with that. Indeed, it might be quickest to just go go one step too far. Right. What happens if I go... Right, it is willing to do that. Good. So that's correctly initialised the 2 stacks in the way that Simon suggested. So that then gets up to the point where we're then waiting for this node to do something useful. So this one similarly should signal, right, I'm ready. So this node will then do something like that. So that's a slightly weird. That node is almost entirely just doing synchronization. So then we have the slightly confusing thing that we really would like these two stack memory nodes to be closer together. So that initializes the two stack memory nodes and then halts, waiting for this processor, which has received an 8 from up there, to work out what to do with it. So can we remember what Simon's plan was for this one then? The plan was... Oh, the plan actually requires two nodes, doesn't it? Because it needs two accumulators. I think we've built this whole thing left, right, reversed. We'll fix that later. Because what we want to actually happen here is this one needs to do the repeated subtraction. So that one gets that in, subtracts something and goes, and then needs to check, is that... So if it ends up less than 0, that means that we've gone too far. So if it doesn't end up less than 0, then that was a good situation. Hang on, we've got to, let's call that X, for we've gone too far. Then we go back up to the loop. If we find ourselves having gone too far, so if we haven't gone too far, we need then to signal to the node on the left that it should add from its stack. Otherwise, we need to signal to the left, to the node on the left, that it should not add from it, it should discard from its stack. So then this one then ends up being controlled by the one on its right. And if it's adding, then it should go. It probably needs to like do some initialization, doesn't it? Or it might be discarding. So, initializing the contents of the stacks. I'm just going to swap those two instructions around because it's embarrassing that they're that way around. Obviously this one will finish first, so we should wait for it first. What? No, that's wrong. And like, apart from the fact that everything's seized up, we have successfully calculated that 1 times 8 is 8, which might seem like a really easy thing to calculate, but we did actually do it by quite a complicated procedure. So it's not like this is an entirely trivial result. So that's doing quite well. So now what do we need? We need some way of something signalling that we've reached the end. Which is kind of tricky, actually. Because, like, we're pretty dependent on like, because this does have to be a loop. I am slightly wondering how much of this we can just unroll. But the thing is that we need at least 4 iterations of the loop in order to be able to cope with numbers up to 8. And note that we have at least 1 9 in here. So we do need 5 iterations, which means that we can't fit a loop this complicated unrolled. But thus, how do we signal to this node that it has reached the end of the multiplication, i.e. that this stack memory node is empty? Because all that it does with the values it reads from that stack memory node is to subtract them from the accumulator. I suppose one possible approach, we are less than half filling that stack memory node. So we could alternate in that stack memory node things that say whether this is the last entry in the stack and the actual data, and that could then drive this in a standard microprogrammed approach. So it's a stack, you idiot. Also, you didn't need to do it that inefficiently. Also, it's stack, you idiot. 9 is the sentinel value and should go at that end of the stack. Right, and now everything actually wedges at the point when we have an answer. So then we need some code to sort out having an answer. Like that. I mean, we don't have any stuff to process the next number. Oh, and we seem to have crashed. Have I forgotten something? Yes, I've forgotten to have this one signal leftwards that something needs to happen. Still didn't work. Yes, it did. 8. Right. So it manages the first sum. So now, once that has sent its output, it should reset the accumulator and then loop back up to the top. So that's fine. This one, once it has calculated a result, then has to signal upwards that something has happened. So rather than JRO 0, it should do mov nil up to signal to this one that it's time to start doing things again. Right. So what happened there? Right, so we're now at the end of doing the first multiplication. This processor will now signal leftwards to emit the result. Then it signals upwards that it has finished and the stacks should be refilled. So there's that signal going upwards. This one should then signal left and right, and both of those processors are now waiting. Oh, right, that one currently crashes at that point rather than doing anything. That's what our problem is. That's fine. We can just remove that last instruction. Well, thank you, Simon. Your idea seems to have worked. Let's see how it looks on the graphs. I mean, possibly we could do slightly less gratuitous loop unrolling, but also I think we don't need to go all the way up to 16 if all of our inputs are single digits. Obviously we need to work out how to make this faster, but well, yes, we can't. It obviously has to be serial in that we have to fill the stacks and then empty the stacks. We can't do those in parallel. That bit is, I'm afraid, like we solved that in the previous one by using twice as many stacks, but we don't have 4 stacks here. Though, maybe there's some terrifying way in which we could do this only on a single stack by having it alternate the values from the 2 sides. Don't really want to try that though. Because, I mean, this one, which does most of the thinking, is running at only 40% idle. Really, we want a profiler here now. But yes, that seems to be working correctly. I should tell Simon that this works. So way off to the right on instruction count and node count, and our cycle count isn't that good. Hang on, our cycle count has got worse. Well, that's embarrassing. We are in all respects worse. Well, let's at least try to tighten up the cycle count a bit. So we don't need to do 16s because none of our inputs is over 16. So we can remove those instructions. That'll make it a bit faster. Similarly, we've got this lot the wrong way round because we should have the common case first and the commonest case. No, we should have the common case last, and the commonest case is clearly ignore things because most of our inputs are small, I think. So that's 3 and has a jump 0 after it, and that's 6 and should not, because wrapping around is cheaper. So what was 3 should now say 6, and what was 5 should now say 3. I think that's a bit faster. So still at 2439. And now going, is there some... So in all cases, this one signals leftwards before it does everything else. Like basically, as soon as it's made a decision, it immediately sends a signal to the left. So that maximizes the parallelism we can get there. And these similarly fill up in parallel. So, I mean, we can try doing what Simon suggested and limit how big the stacks get, but that doesn't feel like that's going to require extra code in the stack filling sections. So if there were any... I mean, there's an obvious... We can reduce the number of nodes by 1, but that really doesn't help us much. And things could be slightly more efficient by by reflecting the whole thing around the vertical axis so that we output straight down rather than having an output through this L shape. But that's quite minor given how slow this is. I'm now pondering the possibilities that loop unrolling might offer. But it's kind of tricky, because what I was thinking was, could we use JRO based on one of the inputs to jump us to the correct point in an unrolled loop to add the right number of the other input. The difficulty with that is that fundamentally we have to add a value that comes from a different processor. And so we don't know, we can't just have a loop that goes add right, some number of times and then jump into the middle of it, because the sending side needs to know when to stop sending. And fundamentally, the only thing you've got that you can read repeatedly is your own accumulator. And while we can do add ACK repeatedly, that multiplies things by 2, which that only allows us to emit powers of 2, which is not very helpful. So, like, we know that there are many faster things that have been done. So my unrolled loop idea, we could of course have another run of instructions afterwards that discard the spare things, but then we don't know when to stop. Self-modifying code is definitely not on. And we have to, if we're doing things by repeated addition, we have to be in a position where if where we know when to change what value we're adding. And like similarly, if we swapped it around and had a node that sent things to be added, then it would need to know when to stop sending zeros in the same way. Ooh. Oh, this is so close to working. Except, I mean, obviously it gets the wrong answer because we're trying to use the accumulator for two things. But that's fine, we've got more accumulators lying around. Idiot boy. Those should all say up. And those should all say left. I mean down. Should be correct. Then what's wrong with that? Oh, that one crashes at the bottom because it doesn't know what to do next. What? Oops, I should have paused that. So, well, I should let it run and then we'll see what it gets wrong. So everything was going fine until it was tried to calculate 3 times 3, where it got the answer 13 instead of 9. What? And it was just after it had calculated 7 times 0 equals 0. Ah. It was accidentally landing on the wrong entry in this loop, which screwed everything up horribly. So with a bit of gratuitous loop unrolling, things have turned out quite a lot faster. No, we can't save. I was just wondering if there was a way we could make this use 4 nodes rather than 5, but I don't think we sensibly can. Just staring at this briefly to see if there's anything that could be made slightly cleverer, but I rather doubt it. It's not quite Duff's device, but it has some similarities. How do I name these anyway? No. That just drops me back in there. Huh. Because I'd quite like to be able to say, look, this one should be called Simon's one, which is really slow. This one should be called Clever Unroll Loops, or possibly, as Jacob puts it, -F Unroll for all the family. And this is like the naive and obvious one. And we're still not as fast as people have achieved. It's the answer. You have to rename the save files. Put a line in a node with ## at the beginning. Thank you. Obviously, it's in the manual, but yes. Sorry, you can't have the full version there. It was meant to be Simon's clever one, but it doesn't quite work. Yes, I suppose so. Right. So yes, so that was kind of successful because being clever turned out not to be quite as good as just being fast. In the stupid fast program did a lot better than the clever one, which is doubtless asymptotically a good plan, but sadly not when your largest numbers are 9. I mean, we're still not at the right-hand end of the cycle count graph with that one, at least. Right. Well, it's 4 minutes to midnight, so that's probably a sensible point at which to stop. Even though, having previously done 11 challenges in the first 11 segments in the first session, we've achieved 2 in the second session, but we have got 5 solutions in total. Yes, you're quite right, Pink Beast. That is entirely the premise of Roadrunner. So yes, and then next time we start dealing with pictures. Yes, this thing has a graphics subsystem. It's kind of weird. So yes, we'll see you next week. In the meantime, good night.